Hi, me again, back in the campus podcasting room, at least for a little while more. I'm not a huge fan of limit tricks. I mean, this is just my experience, but we learn to take these very special limits using these very specialized tricks, and then we finish the material and we never use it again, and it feels a bit, what was this for? So I'm not going to dwell on this, but this is very standard material, I would say. It's in all the textbooks. And I'm talking about limits of rational functions. And you might say, hold on, in a previous video, you told us how to take limits of rational functions. You said they were just like polynomials in the sense to take the limit as x approaches c of a rational function, p of x over q of x. You stick c in. It's p of c over q of c. But that rule has an asterisk next to it because you can't divide by zero. So if q of c equals zero, this rule doesn't work. So what about what about this? What about when q of c does equal zero? Well, there are only two possibilities. Um, Case one, I'll call it, if P of C does not equal zero, this is the top here, this is the numerator, and the denominator, Q of C does equal zero, the limit does not exist. For example, the limit as x approaches 2 of x squared plus 1 over x minus 2. If we try to use the rule we have written up here, that if we try to just plug 2 in, we get 5 divided by 0, and the limit does not exist. And visual learners can take a look at the graph to see what's happening here. There is a vertical asymptote at 2. If we approach 2 from the right, this function crawls up the vertical asymptote and goes to positive infinity. If we approach 2 from the left, it crawls down the asymptote and goes to negative infinity, but in neither case does it approach a number. And I want to emphasize that the problem we're having here isn't the division by zero, because division by zero happens at 2 itself. And when we take a limit, we don't care what happens at 2 itself, right? I mean, we've already seen an example. It was something like the limit as x approaches 3 of h of 3 minus h of x over 3 minus x. where h is a height function and this limit gives a velocity. We've already seen this example, and this example also has a division by zero error in it. But when we did this example, we found that the limit existed. So it's not the division by zero exactly that's causing problems here. Um, it's having this 5 divided by 0. Like if we go back to the height example, to the velocity example, notice that as x approaches 3, the denominator is going to 0, but so's the numerator. So this limit exists, and it's 0 over 0. This limit doesn't exist, and it's not 0 over 0. I feel like maybe I'm rambling a little, so let me just write down case 2. If the top and the bottom both equal 0, the limit may exist. And what you do in this case, you let's see. Let's correct that to P of C and Q of C. And the limit we're talking about is the limit as x approaches C. So how could we find the limit here if it does exist? Well, it's a trick. Um, it's a trick based on a theorem of algebra, which says that if p of x is a polynomial and p of c equals 0, then p of x factors. P of x is x minus c times some other polynomial. And of course, exactly the same thing for q. If q of c equals 0, then q also factors as x minus c times some other polynomial. And if we've got p of x divided by q of x, and p of x factors in this way, this pen has served me well, but it's on its last legs. If p of x factors in this way as x minus c times a polynomial, and q of x factors in this way as x minus c times a polynomial, well, what happens here? These x minus c terms factor. And now maybe we have a limit of, now we definitely have a limit of a rational function. And maybe we can just use the rule we talked about in the last video. Maybe the denominator is no longer 0. And if this is in any way cryptic, we probably just need to do an example to clarify things. So let me look for the example. Let me pause this while I look for the example in my notes. So this isn't the example in my notes. It's slightly more complicated. But the limit as x approaches 2 of x squared minus x minus 2 over x squared plus x minus 6. So the first thing we try if we have a limit of a rational function is that we just stick 2 in there. Well, we stick c in there. In this case, c equals 2, because if we don't get a division by 0 error, that will give us the limit and we'll be golden. Now, in this case, 2 squared minus 2 and 2 squared plus 2 minus 6, we do get a division by 0 error, and the top is 0 as well. And this means that this limit might still exist. Getting a division by 0 error doesn't tell us that the limit doesn't exist. It just says, well, we need to do additional work. And the suggestion, if you want to think of it as a suggestion, the method that we use is to factor and then cancel the polynomials. When we get 0 divided by 0, like we do here. Factoring polynomials can be quite cumbersome. Obviously, this problem was developed in a lab, as it were, to factor nicely and easily. This is x minus 2 times x plus 1 over x minus 2 times x plus 3. X minus 2's cancel. And now we've got a limit of a rational function. And the thing to try when you have a limit of a rational function is to take your c value and stick it right in. Here, that didn't work. It gave us a division by 0 error. But here, now that everything is canceled and we have x plus 1 over x plus 3, 2 plus 1, 2 plus 3, the limit is 3/5. This is, I maybe downplayed this material slightly at the beginning. It is a trick. We're not going to be doing this in like week 4 of the course. We'll have moved beyond it, but we will be using this trick in at least one future section where we're computing derivatives. This is differential calculus. Derivatives are the thing that we're studying. So you ought to have a handle on this. And with that, I think this video is at a close. See you in the next one.